All right, good morning. Any questions, any comments? So I want to talk about Ginzburg-Landau. But in this case, I'll start talking about a non-uniform superconductor. Okay. So let's remember what we did last time. Last time, in the uniform case, we introduced an order parameter, and it was like a psi, which was just like a complex number. It was non-zero in the ordered phase and zero in the disordered phase. And we found it as a function of temperature, for example. But here, in the non-uniform case, we will promote this parameter to a function. This is psi of r. Now we need to optimize some kind of free energy to find a function. So we are not trying to find a parameter, we are trying to find a function. So this is complex valued function. Good. So maybe I can remind you, like Lagrangian mechanics, like in the classical mechanics, we have a Lagrangian L which depends on x and x dot. Why does it only depend on n and x dot? Why would it not depend on anything else?
The only other thing can be time.
Yeah, it can also depend on time. I can put it time, but for the moment, let's think about conservative systems, and there is no time. The question here is, why don't I have, for example, second derivative of x? Is it allowed?
In principle, yes.
Yeah.
But in a second order system, you need to go one step lower.
Exactly, right? We typically want to expand our action to lowest order. And this actually describes nature. For example, if you want to look at a particle in a potential, this amounts to 1/2 m x dot squared, right? Lowest order is not x dot, it's x dot squared, right? If you had like x dot term here, that would break the good symmetries we require here. So we start with x dot squared, and there is some v of x. And v of x is generally like, you can think about harmonic oscillator. And what you do is you minimize this, and you find del x is equal to minus del v del x, del l del x dot is equal to m x dot. And if you take the derivative here, d dt, it is m x dot. And Euler Lagrange, so this Euler Lagrange gives you m x dot is equal to minus del v del x. And what is that? That's the Newton's second, right? So we will do something like this. So what we are now considering a superconductor, like superconductor, and expand. Let's consider free energy density, Fs, up to psi to the fourth, right? So exactly like this classical Lagrangian, we are also allowed to have derivatives, right? So I can, like, let's start Fs. It depends on temperature, and it may depend on other things. There's like some constant which we call it F normal T. This constant in the sense that it doesn't depend on the order parameter. Plus maybe some, let me call it alpha, the gradient term, right? X dot here is replaced with the gradient because this psi depends on x, y, and z, a three-dimensional vector. So this is psi squared, and the others are exactly the same. There's like some b psi squared plus maybe I think we called this A previously, this is A, and a half B psi to the fourth. But now these are like functions, right? This is a free energy density, this depends on R. If you want, this is R dependent. And typically, I can write this parameter whatever I want, and the Ginzburg and Landau, they used h bar squared over 2m star, right? Rather than alpha, I can define a new constant here, m star. And you will see in a little bit, this will make a lot of sense. And in the following, let me also drop m star and just write m, but let's remember this is not the physical mass. Good. Therefore, if this is the free energy density, exactly like Lagrangian density, we can find the free energy by integrating. So F superconductor, again it is like T, but at some point I'm going to stop writing. There is like this constant F normal T plus integrate over all space D cube R, and you need to plug this in. Good. How many people know something called like functional derivative? I think if not, it is kind of like a derivative, but it is functional. Let me just introduce it to you. Suppose, let's think about, suppose I have some xi, and this means x1, x2, x3, and it can go on if you want. And what we want to do is like, for example, del x1, del x1, what is that? This is 1. Del x1, del x2, what is that? This is 0, they are independent. Similarly, then I can just do del xi, del xj is delta ij. I can also look at, for example, del xi squared del xj. I just take the derivative to xi delta ij, and I can look at any function of xi, del f of xi del xj is going to be f prime of xi and delta ij. Good. Now we can think about this, but like if you want this psi, let me write 1x, but it can also depend on y and z. So we can think about this like on a grid, psi of x1, psi of x2, dot dot dot, psi of xn. And we can consider some x to go to, I don't know, some xi, some x prime to go to xj here. And now sometimes people use this notation for functional derivative. So this is psi of x del psi of x prime. What is that? Right, with our exactly like this prescription. Right, exactly. So this is delta of x minus x prime. Is there any problem with this? Anybody? Right? This is trivial. Okay, good. Very nice. And since our order parameter is complex, we also have to think about things like this. Del psi. Now, since this is trivial, I can easily replace this r, right? This is r prime. This is going to be r minus r prime. But we also need to think about derivatives with respect to complex conjugate. Let's also write that. For example, what is this one? Del psi star of r. Let me call it r prime. 0, right? A number and its complex conjugate are independent. So this is 0. And I think we are, if we have like a functional is a function of function, right? If we have psi of r and del psi of r prime. You just take the derivative here, derivative functional if you want. This is psi of r delta of r minus r prime. Good. Then let's think about things like this. Consider like integral dr psi. Let's do psi to the fourth because psi to the fourth is a little bit trickier. So it's psi r to the fourth, but we know this is equal to let's write this like is equal to psi star squared and psi squared r, and I want to take functional derivative of this like this. So del psi star r prime acting on this thing is going to be equal to this thing dr, right? I take the functional derivative. This is 2 psi star of r. Now there is like delta r minus r prime psi squared r. Then this is automatically 2 times. Let's combine, right? The integral is going to go, and I can write it like psi of r prime squared times psi of r. And if you get that, I think that's almost there. Let's also consider the gradient term. Consider gradient term. Now we have something like this. There are like some constants, but let me not write them. So this is gradient of psi, absolute value, right? And this is equal to dr del psi star del psi. So what do? I'm going to take functional derivative with respect to psi star, but I don't want this gradient of psi here. What is the thing to do here? What's that? Or integration by parts. Exactly, by parts. I want to carry this gradient to here so that I can take the derivative with respect to here. So this is by parts is trivial because at the boundaries we are thinking this field or order parameter to go to 0. So this is going to be dr psi star of r gradient of psi of r. And now I can take the del psi star of r prime of this thing, and this automatically gives me, I will get like a delta function from here, and there's like a minus. This is minus gradient squared psi of r prime. Good. Then our job is to minimize this f. Let me write this one more time. Let me take this guy. So I want to set del f del psi star of r prime. I take the derivative and I want to find the optimum point, so I will set it to 0. Then from the first term I'm going to write exactly like this. I have minus h bar squared over 2m del squared psi. It is r prime, but after I'm done, r prime, they are just label. I can change it any way I want. Plus, so this one is going to give me a psi, plus this one is going to give me b psi squared times psi is equal to 0. Good. Any questions? So this is what we call, if you want, nonlinear because of this term, Schrödinger equation. And because it is nonlinear, superposition principle does not apply anymore, right? And you should also compare with Gross-Petersky. Good. Now I want to solve this equation for some simple example geometries. Let's consider surface of a superconductor. So physically, we always have finite samples, and superconductor always going to have a surface. And if this is x, suppose this is x is equal to 0. This side is suppose superconductor, and this side, let's say, is vacuum. Because inside vacuum there can be nothing. Therefore, I anticipate what am I sketching? I'm sketching order parameter. And for this problem, I can assume it to be a real function, right? We don't need a complex phase here. We'll have problems where we also need the phase, like Josephson effect soon, but not at the moment. Here, superconductor, there is nothing, it's the vacuum, it's 0. Deep inside, I need to have a bulk, and the bulk should not know anything about boundary. And it should be like this uniform case we did last week. So it should be something like this. And I should somehow connect this to this, and this is typically something like that. Right? The order parameter goes from 0 to some finite constant value. And let's write this in using equations. We already have the equation there, and there's only you can see there's only gradients in the one direction, right? And the x direction, y and z directions, they don't matter here. So then I'll write this as minus h bar squared over 2m d squared dx squared psi plus a psi plus b psi to the cube is equal to 0. Assume psi is real here. So this is a second order differential equation, and to solve a second order differential equation we need two boundary conditions. One boundary condition is psi 0 should be 0. A second boundary condition, psi infinity, should be this psi naught, the bulk superconductor. And the bulk superconductor we did last week, right? This psi naught was found to be minus a over b. So bulk order parameter. Hopefully you know this terminology, bulk, right? If it bothers you, we can talk about it. So what we need to do for equations like this, we need to put them in a dimensionless form first, so that we can solve it a little bit easily and don't have to carry around some factors. So let me copy this, and I want to divide this with let me use the color. So I want to divide this with absolute value of A, and we know in the superconducting phase A is negative, so I'm going to put minus here, and this is going to be B over absolute value of A. And now I want to divide everything with psi naught. This is psi naught, and this is psi naught. And you can see this thing. So this A over B is so exactly this is 1 over this is 1 over psi squared, right? Yes, good. And now I want to define a function f of x by psi of x divided by psi naught. And I also want to, here there's like a derivative, I want to also define the derivative. So this, let me define this psi, which is going to come out to be coherence length in a little bit. Psi squared is h bar squared over 2m a. Then, so this object psi squared the x squared, I'm going to define a new the u squared, and u is going to be x over psi. Good. Then the equation here became a little bit more palatable. It is f double prime, so minus f plus f cube. And I can put this minus on the other side and write this. So this is equal to minus, and this is plus. And the boundary conditions, f of 0 is equal to 0, and f of infinity is equal to 1. A little bit nicer to work with. How do we solve this? There's only one thing, f and u, and it's second order. The only problem is it's non-linear. If it was linear, it would be nice. How do we solve differential equations like this? Any idea? So, I mean, from my point of view, you don't solve differential equations, right? Nobody can solve differential equations. Somebody gives you the solution and you substitute. Or you put it in a computer and computer solves it for you. But computer will have difficulty with nonlinear equations, so you are a little bit desperate. But this one is a little bit lucky. This is a nonlinear differential equation with exact solution. There is like an exact solution. And typically here is a little terminology for you. The exact solution of nonlinear equations are generally called solitons. Right? We are now going to find a soliton solution in a little bit. Generally, textbooks don't spend time with this. They just say, here is the solution, substitute and see. But I think there's like a nice trick I like. We can go through, and it also has like some physical content. So what I want to do is I want to multiply this entire equation with f prime. So this is f prime, f double prime is equal to minus f prime plus, actually let me combine them, minus f plus f cube f prime. And so this side I want to write it like du f prime squared. Okay, so this is f prime squared, but there is also a factor of 1/2, right? If I take the derivative, I obtain this line. And this side, I write this as du minus a half f squared plus 1/4 f to the fourth. Right? If I take the derivative, I have 2 is gone, f times f prime, this term is check, and this one 4 is gone, f cubed times f prime, this term is check. I can integrate both sides, and I found, let me cancel this 1/2, f prime squared is equal to minus f squared plus a half f to the fourth. Good. Or I can write it like, so this can, I can put this plus, put this minus, and this thing is a constant. Right? I integrate both sides. This is, if you want, integral of motion or constant of motion. But we can find this constant, right? Deep inside the superconductor, if derivative is 0, so deep inside superconductor, f prime is equal to 0 and f is equal to 1. So this is 0, this is 1, and from here we find C is equal to what? I think, did I cancel? I think 1/2, right? So this is 1/2. Then C is equal to 1/2. And now I can write a derivative. F derivative is equal to 1/2. Let me write it like 1 minus 2 f squared plus f to the fourth, and this is squared, and this thing is equal to 1/2 1 minus f squared squared. Therefore f prime is equal to 1 over square root of 2 root 1 minus f squared. Sorry, f squared squared. And also I take the positive root, because deep inside superconductor, if I put f is equal to 1, right, this makes sense. I mean, here in the geometry you can see I'm taking psi to be positive, and this derivative is also positive. So when I take the root here, I take the positive root here. Good. Now this is much nicer equation, right? This is now first order, and first order differential equations are simpler than anything else. Generally, not always. There are some unexpected first order differential equations, but this is not one of them. Let's solve it. This is d. So I want this df to write df du, and I take everything f on the left hand side and everything u on the right hand side. So this is the df over 1 minus f squared is equal to du 1 over root 2. So what is the integral of this thing? Let's see if anybody remembers. Like, Exactly. So this is arctangent. But if you put it in Mathematica gives either log, there's like a log version, an arctan version. You need to tell Mathematica to simplify a little bit, or you can look at the integral tables. So this is arc tangent hyperbolic f, and this is root 2 times u plus a constant. And when f is equal to 0, when u, we can use the same boundary condition. So if you put u is equal to 0, f should be equal to 0. This is 0, then this constant is also 0. Therefore, we found the solution. This f of u is equal to tangent hyperbolic 1 over root 2 times u. So this is the soliton solution. We solved it. We were lucky. But now I want to convert this to physical order parameter. This psi of x is going to be psi 0 tangent hyperbolic x over root 2 times xi, and our xi is defined as h bar squared over 2m a of t. So this thing is Ginzburg-Landau coherence length, or like if you want, this is superconducting coherence length. And it defines, right, in this sketch, so it defines how much it takes superconductor to recover its bulk value from the boundary. That's the how much. And remember, we had a mean free path for a metal. We had London penetration depth, and there was like a third length scale, and this third length scale is this Ginzburg-Landau coherence length. Let me write a little bit of more, and then I'll finish it there, and we can take a break. So we said A of t was equal to A dot times t minus tc. Therefore, this psi is t dependent. Psi of t is equal to, let me write all these h bar squared 2m. I'll also put a dot here, and I want to write t over tc minus a half. Did I get that right? Yes. And typically what we do is we also take out a factor of tc, and I can write that tc to here, and this thing I'll call some constant psi naught, and this thing, so this object, we call it reduced temperature. T is equal to T minus Tc over Tc. And what we are seeing from here is, okay, this is equal to psi naught times T to the minus a half. So as T goes to Tc, this reduced temperature goes to 0, and psi of t blows up, right? Diverges. So this is a typical of second order phase transitions. So this is second order phase transition. So when you come to like this is kind of like water too, right? As you take water to this 3 critical point, there's something called critical opalescence, right? I don't know if you have ever seen these videos. As water reaches the depth, it starts boiling. There's like water, ice, and gas, they coexist. But right at the critical point, it turns milky. It becomes completely white. The reason, what is the reason for that?
Because you turn into a CFT where you don't have a length.
Exactly, right? So the length scale, right at that critical opalescence, diverges. That means the system is the same in all length scales. If the system is the same in all length scales, right, if you send the light, there is a length scale to scatter that light. no matter which color you send. That's why it just scatters all colors, and that's why it is white. But exactly like you said, at this point, there's no scale, right? The system is scale, or another way of saying this is scale invariant. If you look at like a small system or like a system in the size of the universe, you get exactly the same physics because system doesn't know about scale. So this is scale invariant. Or another like fancy way of saying this is conformal invariant. Or there is conformal symmetry right at the critical point. And there's also critical exponent, right? At the critical point, we have like a critical, sometimes people call it critical index, critical exponent, and here we have 1/2. So this is like a mean field value, and hopefully at some point we are going to see how to improve the mean field value. Good. Any questions? So there is one more little calculation, but let me not do it and assign you as like a exercise. So exercise, if you have the appetite to take some integrals, consider the surface energy. So as you can see, there is a cost of having like a boundary, right? Once you have this surface, there is like a cost because this gradient is going to increase your energy, and the system, if has the boundary, it has to pay for this surface. Or suppose you have like a bulk, right, and you want to form like a surface like this, you have to pay this energy. It's like energetically unfavorable to have these surfaces, but it can be like entropically favorable in some cases, which doesn't concern us at the moment. But let's consider surface energy, and the book is using sigma for this, and what you need to do is you need to integrate this dx h bar squared over 2m dx psi squared, or actually I don't need absolute value, this is also well, plus a psi squared plus 1/2 b psi fourth. And from here I want to subtract the bulk contribution, and the bulk contribution was, if you remember, something like minus 1/8 pi hc squared, and minus of this is plus 1/8 pi hc squared. And this thing is actually, we found like something like minus 1/2 b over a, or something like that, right? You can do the minimization and find this term in terms of a and b. And now psi is here, psi, this psi. So this psi is given here. You can plug in, right? There's like tangent derivative, there's tangent square, and there's tangent to the fourth, and there's some constant here. And Mathematica takes all of these integrals for you. You just need to like organize the parameters and put this integral in a dimensionless form. And at the end, what you find is something like this. Well, I found 1/8 pi hc squared times 1.89 psi of t. So this is energy cost for surface. Good. Any questions? Maybe we can take like a 5-10 minute break and continue.